Okay, so now I have a cool, another cool theoretical example here on my computer program. And so with this one, I just made this a very, very simple reaction. A goes to B, and then B goes to C. So you could see B here is my intermediate. So it's not as complicated as this reaction, but it's nearly identical, right? Where as soon as I make a B, that B can go on and react to form C. And I've got two different rate constants here. And now in this theoretical model, instead of saying slow and fast, I can actually use this handy little manipulate feature that I showed you in the last video to actually like put numerical values on here. So first thing we should do is put some A molecules in here. So you can see, there we go. I've got about 1 molar of A. And you can see nothing is reacting because my rate constants are 0. So now if I turn on K1, you can see now I start making the intermediate B, but I'm not making any C because I haven't turned on K2 yet. And now when I turn on K2, there you can see I've started making some C. Okay? And so now this gets complicated. In this situation where both of these have roughly the same rate constant, so you can see if I make both of them 0.6 and 0.6, it's not straightforward what the overall reaction order is because there's not a clear rate determining step, right? They're both proceeding at about the same rate. And that can happen in chemistry, by the way. It doesn't always have to be one step is slow and one step is fast. It could be that the first step is fast and the second step is slow. Or it could be that both steps proceed about the same rate. That would be a very difficult mechanism to study. So the classic easy examples we start with are in the case where the first reaction is slow and the second reaction is fast, just as our introduction to mechanisms. So now if I were to do that, let's say I crank this K2 all the way up. So I made that K2 go up as fast as I can in my model. And so now you can see that that does not allow a whole lot of B to accumulate. And that's kind of to be expected, right? If this first reaction is slow and the second one is very fast, the instant you create your intermediate, it gets consumed. So you never get to create a whole bunch of the intermediate. And that's why this is very difficult to do experimentally, because maybe you want to try to measure that intermediate, like you want to see it in a spectrum or something like that. But it never really accumulates. So that would be very difficult to do. But now what I also wanted to show you here is now where I've got this K2 at a very high rate, if I start playing around with this number, so here you can see I'm going back and forth from like 7 to 10. Look, it doesn't change the reaction at all. And that's because this K1 is my rate determining step. So when I have, right, the situation, slow reaction, fast reaction, the fast reaction does not matter, right? I'm changing its rate constant all over the place and nothing's happening. But now what happens if I start to approach the K1 rate constant? Okay, so now you can see, even though it's like twice as much, now you can see when I mess with that thing, it is changing the reaction profile. And similarly, now if I change this K1, so if I go back to the situation where K2 is very large, and right when I played around with this, that doesn't affect the rate at all, not by very much. You know, we saw it move just a little bit. But now if I play with K1, you can see I'm not changing it by very much, and it's affecting the reaction enormously. Okay, so those rate determining steps are super important. Okay, let's move on. So now we've got just another example here to do. So let's suppose that I've got this overall reaction. 2 NO2s makes 2 NO plus O2. And someone told us the observed rate law was given as K NO2 squared. So that means perhaps somebody plotted 1 over the NO2 concentration with time, and they got a beautiful straight line, right? So all those dots maybe represent actual experimental determinations of concentration. So someone determined this is second order. So now you can use that information to figure out the proposed mechanism and what must have been the rate determining steps. And so here is now a proposed mechanism, And again, proposed, it means theoretical. It means like we can't know it for certain, so we propose it. We make a hypothesis. Okay. So in one mechanism, someone proposes that two NO2s react to make an NO and an NO3. So that would look something like this, where I've got my two NO2s, and I'll just line them up next to each other, okay? That might not be their correct orientation, but we recognize those two things will react, and it makes an NO and a NO3. And so if I was guessing at this reaction, then that means, it probably would be something like one of these oxygens, right, goes on to form a new chemical bond. So that's going to be my NO3. And so now that means that one electron's got to go that way and the other electron's got to go that way. So that would end up with now an NO3, right? 1, 2, 3, and an NO. Now they're saying this NO3 can further decompose into NO and O2. What would be the rate determining step? Well, because someone observed the rate law to be KNO2 squared, that square means second order, which also means bimolecular. And so here we can see two NO2s right there. So this would tell us this has to be the slow step and this has to be the fast step, because that slow step is giving us the rate determining step. If we were to measure the activation energies for a mechanism such as this, we would actually also see two transition states, because there's two steps, right? So in this first step, where it starts with two NO2s, we would go through this intermediate, our activated complex. Same thing as saying like our intermediate, our short-lived intermediate. So here you can see that activated complex is kind of what I was drawing here, where it's like an NO2 is, they're sharing this oxygen atom, right? So that would be our first barrier. So that gets over the barrier and goes down to now NO3 and NO, which we can see right there. And now it has to go through another crazy looking activated complex, which now, because we've determined that this first step is the slow step, it makes sense that it's going to have a bigger activation energy than the second step. And then it can finally go on to form the stable reactants. Okay. So again, this is all theoretical stuff. This can be very challenging to do, but it requires a lot of base knowledge of chemistry, chemical intuition, to really start kind of guessing at these things and then confirming what we see with experiments.